Hiya folks! In this video we'll have a look at how you can determine the critical angle of a material experimentally. In order to do that, we're going to need a ray box, we're going to need a semicircular block. Now the shape of this is important, which we'll talk about a little later, and we will also need a protractor to measure any angles, as well as a pencil and a ruler. So the first thing we're going to do is put the semicircular block into the middle of the page and then trace around it with a pencil. And this is just so that we can remove the block and put it back into the same position. Then we're going to identify a central point along the long straight edge of that block. This point is going to be where we're directing the beam of light. So that means we're going to need to draw a normal to this point. Your normal is always drawn at 90 degrees to the surface of the material. So we need to make sure we use a protractor and measure that out carefully. We can then replace the block and then turn on the ray box. First we'll have a look at what happens as we direct the beam of light towards the block when we're moving from air into the glass. So what we should see is that when the light is travelling from the air into the glass block, we get a very small amount of reflection, but the majority of that light is refracted. Even as we start to increase that angle of incidence, we always get some refraction. So now what we want to have a look at is, what if we were to look at the ray of light coming from inside the glass and travelling out into the air? So to do that, I'm going to change the direction of the light so that it is now entering the block from below. What I'm really interested in here is the light that is travelling inside the glass block. Then it hits the boundary and it exits the block into the air. So this is where the shape of the block comes into play. By using a semicircular block, that allows us to control the beam of light that is inside the block. Because as long as we direct that beam of light towards that central point on the long edge of the block, we will always be approaching that curved edge along the normal. Because when we have a curved edge, the normal is drawn at 90 degrees to a tangent to that curve. Therefore, we will not have any change in direction. The light will still slow down as it enters the block, but it will not change direction. So we can very easily move the ray box and control the ray of light that's inside the block, and then observe and measure what happens outside of the block. So first thing we'll do is we will shine the ray of light along the normal, so we have an angle of incidence of 0 degrees. Then we'll gradually increase that angle of incidence. What you'll see is that we have refraction occurring as the light exits the glass block and enters into the air. The more we increase the angle of incidence, the more the angle of refraction also increases. What you may also begin to notice is that there is a reflected ray also present, but most of the light is being refracted. If we continue to increase that angle of incidence, we can get the maximum angle of refraction, which is 90 degrees. And if we go beyond that, then no refraction occurs and all of that light is reflected. Now remember, there's no reflective surface here, there's no mirror. All we have is the glass air boundary. And this process is called total internal reflection. All of that light is being reflected, but only when it's above a certain angle. So that's what we want to try and find, and this is called the critical angle. So we want to very slowly increase that angle of incidence until we get that maximum angle of refraction of 90 degrees. Now it is very tricky to see, because that means that the ray of light is actually travelling along the straight edge of the block. Around the same time, that reflected ray will also get brighter. So when you've identified this angle, we can mark the incident ray with a couple of crosses. The refracted ray is quite difficult to see, it's running along the edge of the block, but we could also mark on the reflected ray. Then, when we remove the block, we can use a ruler to draw lines to show where the ray of light went while it was inside the block. We can use a protractor then to measure this angle. This angle is the critical angle. So lining it up with the normal, this angle works out to be 42 degrees. So that means that an angle of incidence of 42 degrees will cause an angle of refraction of 90. We could also draw on the reflected ray and then measure the angle between the incident ray and the reflected ray. Now this angle will actually give you 2 times the critical angle. So once it's measured, we need to remember that that angle would need to be divided by 2 in order to tell us what the critical angle is. And that's also making use there of the law of reflection. In this case, the angle between the incident ray and the reflected ray is equal to 84 degrees, which means that the critical angle, which is half of that, is 42. So now we'll have a look to see how the critical angle is related to the absolute refractive index of the material. So let's remind ourselves what we just determined from the experiment. We find that as the light travels from glass into air, then there is a specific angle of incidence which will cause an angle of refraction of 90 degrees. That angle of incidence is what we call the critical angle, and I'm going to use the letter C for that. That will cause an angle of refraction that is equal to 90 degrees because it was running along that flat edge of the block. So now we're going to take those values and we're going to put them into the equation for Snell's law, which is n is equal to sine I over sine r. Now in this case, I is equal to the critical angle, so that means we have sine C divided by sine r, which is 90. Now there's one thing we need to be very careful with here. Because our angle of incidence is in the glass and our angle of refraction is in the air, then the refractive index we're working out is not the absolute refractive index, because it's not going from air into the glass, but rather we have glass going into air. So really this should be written as a subscript G, then N for refractive index, and then subscript A. So going from glass into air. To get the absolute refractive index, meaning we want to go from air into glass, then it's the inverse of glass into air. So that means we have 1 over the refractive index for glass into air. So that means we need to take the inverse of the equation that we've just written out. So instead of having sine C divided by sine 90, what we've actually got is sine 90 divided by sine C. Now we could take that sine 90, put that into a calculator and work that out, and that's actually equal to 1. So that means really what we have is 1 over sine C. Now normally when we're talking about the absolute refractive index, we don't put those subscripts on. We normally just write n. So anytime you see the n on its own, we assume that it's the absolute refractive index. In this case, going from a vacuum or air into glass. So n is equal to 1 over sine C. Another way of looking at that would be to use the fact that we know that light rays are reversible. So as we go from glass into air, we know that our angle of incidence was equal to the critical angle and the angle of refraction was equal to 90 degrees. However, if we were to reverse the direction that the light was travelling and we were to go from air into glass, then if we have an angle of incidence of 90 degrees, that would result in an angle of refraction that was equal to the critical angle. Now, using that information and putting it into the Snell's law equation, where n is equal to sine I divided by sine r. Well, sine I is equal to 90 degrees. So we have sine 90 divided by sine r, which in this case is the critical angle. And now we've got the same scenario that we had before, where sine 90 is equal to 1, so therefore the refractive index is equal to 1 over sine c. So that's two different methods of arriving at that same equation, where we have the absolute refractive index is equal to 1 over sine c. Just be very careful that you pay attention to which direction the light is travelling in and which version of the refractive index that you're using, whether it's going from air into glass or glass into air. So that's it. I hope you find that useful.